Okay, let's finish up gravity because we're going to talk about dark matter. And you got to get to dark matter. That's like the most exciting thing in the universe. Actually, it's the least exciting thing in the universe because we can't see it. Okay, so universal gravitation, we did it. We talked about unit vectors. It was a mistake. Don't worry about the unit vectors, okay? Just think about the forces. Remember, gravity is attractive. Whenever you're dealing with the forces, it's always attractive. So as we do our calculations next, you'll see all I'm doing is saying it's attractive. We won't panic about the radial unit vector. Local G, hopefully you had some idea what I meant. Read it in the book if you didn't. But universal gravitation that Newton discovered, F equals big G, mm over r squared. That's everywhere in the universe. Little g is just this little provincial thing we have here on the surface, F equals mg. Your weight equals mg. So it's just a translation from how the universal formula shrinks down to the little F equals mg that causes the chalk to drop. And I can't get more because I don't want to deal with the poster. Oh, let's see. Oh, it's a big risk to mess with the poster once it's up. Oh my God, there we go. Okay, thank you. And I thought that was applause. Okay, so now we're going to do dynamics and talk about orbits and height and how things move. Because in gravity, so if you're near the surface of the Earth and it's just something dropping, if it's just the weight near the surface of the Earth, we've done those dynamics for 3 weeks. Right? That's what we did all last week and in kinematics. But we want to think about dynamics of larger things moving around, right? So what we want to think about is when we were throwing things. When we did the shoot and drop demo or experiment. We had it here and we shot something, that little square aluminum thing, we shot and it fell like that. And we said, what if we shoot it harder? It'll fall like that. Harder, it'll fall like that. And we said it'll always fall in the same amount of time as the one that drops because they're falling the same amount if you ignore the curvature of the Earth, right? So we were just dropping something where you can see it drop, right? Something like this, you could kind of see it drop. These damn aerodynamic darts here, they're down, right? It's falling down. Or you can see it drop if you do that. And it drops, there we go. But if something goes like really fast, remember this goes so fast you can't see it drop, right? This just goes straight ahead. It actually went up a little bit. Okay, I'm going to hit the light. Here we go. Ooh, almost. I'm going to hit that water bottle right now. Hit the water bottle. Maybe I'll set off the fire alarm. Oh, not quite. But you can see if you shoot something harder and harder, what is it doing? It's getting farther and farther, right? Eventually it would see the curvature of the Earth would actually make a difference, right? But what would eventually happen? You would miss the Earth eventually, and you would go in a circle. Eventually. Well, a good circle. Like that, right? That's a funny circle. That's like a perfect circle. So it is possible to achieve orbit which is just uniform circular motion from last time. Circular motion with the force of gravity as Fc, if that makes sense. Remember we said if something's in uniform circular motion, there's a centripetal acceleration in, and you need a force to make that centripetal acceleration. So it's just making gmm over r squared that force. Let's see. So let's do it this way. Let's say near the Earth's surface. Could we put that bullet into orbit? How fast would it have to go? We'd say, okay, we want gravity to equal the centripetal part. Well, near the surface of the Earth, even if you curve around the Earth, it's always going to be mg, right? So if the bullet's mass is m, then you say mg, and that has to be equal to, the centripetal force had to be mv squared over r. Right? mv tangential squared over r. And if we're near the surface of the Earth, that r is big RE, radius of the Earth. So that would seem to have to be true. And then you find out it doesn't even matter how big the bullet is. It's like the masses cancel, as often is the case. So this would tell you if your force is just m little g, 9.8, down, then that's all you got to do. And then you can solve for Vt. V, how fast you'd have to shoot it would be the square root of the little g, 9.8, times the radius of the Earth. And let's think about what that motion would look like. Let's grab it somewhere along the circular part here. What would it look like? It would have mg down, right, because we know the weight is down, and it would be going this way, vt, and that fulfills the requirement for uniform circular motion that those two are perpendicular. I didn't prove this. I said this is true when I made this statement. When I said the force equals the centripetal acceleration, basically said, okay, then you're in uniform circular motion. Okay? So if we plugged in the numbers, and I'll give you the radius of the Earth again, maybe it's an even different number this time. It's a square root of 9.8, that's little g. The radius is 6.37 times 10 to the 6 meters. At least on this page of my notes. That's what it is. Okay? Basically 6.37 million meters. Sometimes you'll see it in kilometers, and they'll say it's 10 to the third. But I usually do it in meters. So if you plug all that in, how fast do you have to go? You have to go 7,900 meters per second. Wow. So if we could shoot the bullet at 7,900 meters per second, it would immediately catch fire and incinerate in the atmosphere, right? So you can't really have something orbiting at sort of a human height above the Earth, because it would run into buildings and trees, and it would heat up due to friction from the atmosphere. It would never happen. I'm not sure what the lowest orbit you can achieve is. But usually also for orbiting objects, you don't really care so much about how fast it's going. You care about how long does it take to come around. Okay? So for the bullets